Have you ever stopped to think that your electronic devices work with the same basic logic for more than 70 years? That's right. Your ultra-powerful smartphone, with its cutting-edge processor, follows the same fundamental principles as the first computers created in the 1940s. But there is a technology that promises to completely revolutionize the way we process information. A technology that doesn't follow the rules of our everyday world, but rather the strange laws of quantum physics. A technology capable of solving in seconds problems that current supercomputers would take millions of years to process. Today, we will explore the fascinating world of quantum computing and understand why it is radically different from everything we know. By the end of this video, you will understand the basics of how quantum computers work, what their real applications are, and why major companies and governments are investing billions in this technology. And best of all, we will explain all of this in a way that anyone can understand without needing a PhD in physics. Before we begin, please leave your name and the city you're watching from in the comments. To understand why quantum computing is so revolutionary, we first need to understand how the computers we use today work. Traditional computers, which we call classical computers, work using bits. A bit is the smallest unit of information and can only take two values, 0 or 1. It's like a switch that can be on or off. There is no middle ground. All the digital information we consume daily, whether an email, a photo, or a YouTube video, is composed of long sequences of these zeros and ones. A common processor performs operations on these bits, following well-defined logical rules. For example, if it receives 2 bits with a value of 1, it can add them and get the result 2, which would be represented as 10 in binary language. This approach has served humanity well for decades. We've been able to create increasingly powerful computers simply by reducing the size of transistors, which are the components responsible for manipulating these bits, and putting more of them on a single chip. In 1971, the first commercial microprocessor had about 2,300 transistors. Today, the most advanced chips contain more than 50 billion. But there's a problem. We're reaching the physical limit of this approach. Transistors are already so small that they're beginning to be affected by quantum phenomena. Ironically, the same phenomenon that represents an obstacle for classical computing is precisely what enables quantum computing. Now let's enter the quantum world. If classical physics describes the behavior of large objects like balls, cars, and planets, quantum physics describes the behavior of very small objects, like atoms and subatomic particles. And at the quantum level, things get very strange. In quantum computing, instead of bits, we have quantum bits. And here's the big difference. While a classical bit can only be 0 or 1, a quantum bit can exist in a combination of both states simultaneously. This is called superposition. It's as if a switch could be on and off at the same time. To visualize this, let's use an analogy. Think of a coin. A classical bit is like a coin that can only be in 2 states, heads or tails. A quantum bit, on the other hand, is like a coin spinning in the air, which in a way represents both heads and tails at the same time, until you observe it and it settles into a defined state. Another fundamental quantum phenomenon is entanglement. When 2 quantum bits are entangled, the state of one is directly related to the state of the other, no matter the distance between them. Einstein called this spooky action at a distance because it seemed to violate his theory of relativity. If you measure one quantum bit and it settles as 0, instantly the other entangled quantum bit assumes a corresponding value, even if it's on the other side of the universe. These two phenomena, superposition and entanglement, are the key to the power of quantum computing. This means that a quantum computer can process an astronomical amount of information all at once. But how does this translate in practice? Let's explain some real applications of quantum computing that could transform the world as we know it. The first potentially revolutionary application is cryptography. Today, much of digital security depends on encryption algorithms that would be practically impossible to break with classical computers. For example, to decrypt a 2048-bit RSA key, a traditional supercomputer would take billions of years. A quantum computer with enough quantum bits could do this in a matter of hours or even minutes. This represents both a threat and an opportunity. On one hand, current security systems could become vulnerable. On the other hand, quantum computing also enables new methods of theoretically unbreakable encryption, such as quantum key distribution. The second application is in the area of discovering new materials and medications. Accurately modeling the behavior of complex molecules is extremely difficult for classical computers, as interactions between atoms follow the laws of quantum mechanics. Quantum computers could simulate these interactions much more naturally and efficiently. This could drastically accelerate the development of new medications, more efficient catalysts for fertilizer production, high-capacity batteries for electric cars, and superconductors that work at room temperature. Some pharmaceutical companies are already exploring the use of quantum computers for drug discovery. The third application is in optimizing complex systems. Many real-world problems involve finding the best solution among an astronomical number of possibilities. For example, what's the best route for a delivery truck that needs to visit hundreds of different locations? How to allocate resources in a global supply chain? How to optimize an investment portfolio to maximize returns and minimize risks? Quantum computers could solve these optimization problems much faster than classical computers, leading to more efficient solutions in areas such as logistics, finance, and manufacturing. The fourth application, and perhaps the most fascinating, is in artificial intelligence. Machine learning algorithms benefit enormously from parallel processing, something at which quantum computers naturally excel. Quantum algorithms for machine learning could analyze much larger datasets and identify more complex patterns, leading to significant advances in areas such as image recognition, natural language processing, and medical diagnosis. Now that we know the potential of quantum computing, you might be wondering, if this technology is so powerful, why aren't we using quantum computers in everyday life yet? The answer is that quantum computing still faces significant technical challenges. One of the biggest problems is quantum decoherence. Quantum bits are extremely sensitive to external disturbances, such as temperature fluctuations, magnetic fields, and mechanical vibrations. Any interaction with the environment can cause quantum bits to lose their quantum properties and behave like classical bits. This is called decoherence. To minimize decoherence, current quantum computers need to operate at temperatures close to absolute zero, about -459 degrees Fahrenheit. This requires complex and expensive cooling systems. Furthermore, even with this extreme cooling, quantum bits maintain their quantum properties for only fractions of a second before experiencing decoherence. Another challenge is the precise control of quantum bits. To perform quantum calculations, we need to manipulate quantum bits with extreme precision. Any error in this manipulation can propagate and compromise the entire calculation. Scientists are developing quantum error correction techniques, but this requires using several physical quantum bits to represent a single logical quantum bit, significantly increasing the total number of quantum bits needed. Despite these challenges, progress in the field has been remarkable. Companies like Google, IBM, Microsoft, Amazon, and various startups are investing heavily in research and development of quantum computers. In 2019, Google announced it had achieved quantum supremacy, performing a specific calculation that would be impractical for the most powerful classical supercomputer of the time. Current quantum computers are relatively small, with a few dozen or hundred quantum bits, and still have high error rates. They are mainly useful for research and development of quantum algorithms, but are not yet practical for most commercial applications. However, many experts believe we are just a few years away from seeing quantum computers being used in specific real applications, particularly in areas such as quantum chemistry and cryptography. And in the coming decades, we can expect to see increasingly powerful and reliable quantum computers capable of solving problems that today we consider intractable. Beyond private companies, several countries are investing massively in national quantum computing programs, recognizing its strategic potential. China announced a $10 billion program to build a national quantum computing research center. The United States approved the National Quantum Initiative Act, investing billions of dollars in quantum research. The European Union launched the Quantum Flagship, a €1 billion program to develop quantum technologies. Other countries such as the United Kingdom, Canada, Japan, and Australia also have significant programs in the area. This global race for quantum supremacy is no coincidence. Quantum computing has the potential to redefine the technological and economic balance of power in the 21st century. The country or company that first develops practical and reliable quantum computers will have enormous advantages in areas such as artificial intelligence, drug discovery, climate modeling, and cybersecurity. It's important to emphasize that even with all these advances, quantum computers will probably not replace classical computers in our homes and pockets. They are designed to solve specific types of problems and are not necessarily better for everyday tasks like browsing the web, editing documents, or playing video games. What's most likely is that we'll see a hybrid model where applications will primarily run on classical devices but delegate certain complex calculations to quantum processors in the cloud. Companies like IBM, Amazon, and Microsoft already offer access to quantum computers through their cloud platforms, allowing developers and researchers to experiment with this technology without needing to acquire the hardware. To conclude, quantum computing represents a fundamental paradigm shift in how we process information. It's not just an evolution of current computers, but a completely new approach based on the strange and counterintuitive laws of quantum physics. Although we are still in the early stages of this revolution, the potential is immense. Problems that today we consider impossible to solve could become tractable with sufficiently powerful quantum computers. This could lead to transformative advances in areas such as medicine, material science, artificial intelligence, and much more. If you're interested in this fascinating topic, consider diving deeper. There are many free online resources to learn about quantum computing, from introductory courses to simulators that allow you to experiment with quantum algorithms without needing a real quantum computer. And don't forget to hit the bell and subscribe to the channel for more content about emerging technologies that are shaping our future. In the next video, we'll explore how artificial intelligence and quantum computing could work together to solve some of humanity's most challenging problems. Until next time.